My post-strike blood pressure dynamics using VPT analysis. VMT and TDA, an interpretation of PP, MAP, and RPP on chronic disease risks. Number 1434, VPT Sharp 007, November 12, 2025. Gerald C. Shu, EclaireMD Foundation. Category, Blood Pressure. Preface. This particular study continues my post-stroke cardiovascular health research using the Viscoplastopology, VPT, models and approach. It combines viscoplastic energy modeling, VMT, and topological data analysis. TDA, modeling to decode the insights of my blood pressure dynamics through three primary hemodynamic stressors: pulse pressure, PP, mean arterial pressure, MAP, and rate pressure product, RPP. The output strain, M3, my third metabolic element related to overall blood. It is defined as normalization factors are: PP is 45 mm of mercury, MAP is 84 mm of mercury, RPP is 7000. This 16-week study, from August 2, 2025, through November 11, 2025, was conducted following my recent hemorrhagic stroke on June 21, 2025. It reflects my ongoing stroke recovery period, weeks from 31 to 46 of 2025. The goal is to quantify my cardiovascular stability, detect any residual imbalance, and understand systemic energy dynamics, by focusing on three secondary derivatives, PP, MAP, and RPP, derived from three primary blood pressure biomarkers, SBP, DBP, and HR. This analysis examines how these secondary hemodynamic variables influence long-term health outcomes, particularly organ-based mortality diseases, including cardiovascular disease, CVD, chronic kidney disease, CKD, neuropathy, retinopathy, stroke, and dementia. Cancer is excluded from this analysis, since it is primarily a cellular-based and largely irreversible pathology. In my medical research, I have intentionally concentrated on organ-based diseases such as CVD, CKD, neuropathy, retinopathy, stroke, and dementia. These conditions involve systems that can still respond to hemodynamic, metabolic, and behavioral interventions, in other words, partially reversible pathologies governed by physics, mechanics, and physiology. In engineering terms, these are dynamic plastic situations, where mechanical and physiological systems can adapt, recover, and restabilize when external stress is properly managed. In contrast, cancer arises at the cellular and genetic level, where stochastic mutations and irreversible proliferative processes dominate. Once the intrinsic control mechanisms within the cell are disrupted, external systemic factors such as blood pressure, glucose, or oxygenation exert limited influence. In other words, most cancer cases belong to the category of fracture mechanics in engineering. Beyond repair and recovery, once structural integrity at the cellular level is lost. Pathophysiological illustration. Blood pressure reflects how well the heart and blood vessels work together. As a mechanical system, it depends on three key physical factors: how strongly the heart pumps blood, how much resistance the blood faces as it flows through vessels, and how elastic or flexible those vessels are. Systolic blood pressure, SBP, is the higher number. In a blood pressure reading, it represents the maximum pressure when the heart contracts and pushes blood into the arteries. A higher SBP means the heart is working harder, or that the arteries have become stiff and less able to expand with each heartbeat. Diastolic blood pressure, DBP, is the lower number. It shows the pressure when the heart relaxes and refills with blood. If DBP is high, it often means the small arteries and capillaries have become narrow or less flexible, making it harder for blood to flow freely. Pulse pressure, PP, is the difference between SBP and DBP. It measures how much the pressure rises and falls with each heartbeat. The pulse wave moving through the arteries. When PP stays high over time, it suggests the arteries have lost their natural elasticity. This constant strain can injure small blood vessels and speed up the formation of hardened plaque, which could block the blood flow. Atherosclerosis. Mean arterial pressure, MAP, represents the average pressure that keeps blood flowing through all organs, with needed oxygen and nutrients. It combines both the high, SBP, and low, DBP, parts of the heartbeat. If MAP remains too high, it puts continuous mechanical stress on organs, such as the kidneys, heart, and brain, which must handle an excessive load around the clock. Rate pressure product, RPP, is calculated by multiplying SBP by the heart rate, HR. It estimates how much oxygen and energy the heart muscle needs to keep pumping. A higher RPP means the heart is under heavier workload and must consume more oxygen. When this condition persists, it can lead to fatigue of the heart muscle, reduced efficiency, and eventually ischemia, poor blood supply. All these blood pressure components are connected. When both PP and MAP rise together, the arteries become stiffer, and the smallest blood vessels experience high stress. When RPP suddenly increases, the heart's energy demand spikes. If these stresses are not balanced or reduced, they gradually damage multiple organs. Cardiovascular disease, CVD, caused by a combination of high PP and RPP, that overloads the heart and thickens artery walls. Chronic kidney disease, CKD, develops when high MAP keeps glomerular pressure elevated for years, wearing out the kidney's filtration system. Neuropathy occurs when small blood vessels supplying nerves become constricted, limiting nutrient and oxygen delivery to nerve fibers. Retinopathy results from repeated PP oscillations that injure delicate blood vessels in the retina, leading to blurred vision or vision loss. Stroke can happen when a sudden surge in PP or RPP ruptures a weakened blood vessel in the brain, like my case of stroke. Dementia tends to appear after years of slightly elevated MAP, which reduces steady blood flow to brain tissues and accelerates memory decline. In summary, blood pressure is not just a pair of numbers. It is a reflection of the heart's mechanical workload, the flexibility of blood vessels, and the continuous energy exchange that sustains every organ. Maintaining stable pressure within a healthy range protects the entire cardiovascular network from long-term structural and functional damage. This understanding of mechanical and physiological balance forms the foundation for the next stage of analysis, using the VMT, viscoplastic energy model, which quantifies these pressure-related stresses into measurable energy components for deeper insight.